What if I told you that just by understanding how to count, you already hold the key to something as complex as trigonometry?
Yeah.
That's what this deep dive is all about.
Right.
Uncovering that unexpected power of algebra.
Right. It's so easy to think of algebra as just like memorizing equations and stuff. But it's
Yeah.
really a way of thinking a framework for solving problems.
Mm-hmm.
And it all goes back to those really basic concepts we all learned in like grade school.
Totally. Our guide for this deep dive is Richard Feynman, and he starts with exactly that. Integers, addition, multiplication, all those building blocks of basic arithmetic.
Right.
You wouldn't think that those simple ideas would unlock the secrets of advanced math, would you?
That's the beauty of it, though. Feynman shows how these like almost obvious starting points, when you view them through the lens of algebra,
Yeah.
they become these powerful tools.
Okay, so let's unpack that a little bit.
Sure.
What makes algebra different than just, doing regular old math?
It's all about this idea of abstraction and generalization. So instead of just saying, okay, 2 + 2 = 4, right? Algebra gives us this language to express the relationship between those numbers,
Right.
no matter what numbers we plug in.
So it's like we're creating a blueprint
Yeah.
that can work in any situation.
Precisely. And this is where things get interesting.
Okay.
Because Feynman's great plan, as he calls it, is to show how, by using the consistent rules of algebra, we can go way beyond these simple integers.
Oh, wow. Okay.
Yeah.
You mean like fractions, decimals, that kind of thing?
Even further than that, think negative numbers, irrational numbers, like the square root of 2.
Yeah.
Even imaginary numbers.
Hold on.
Yeah.
Negative numbers, I get fractions I could handle, but imaginary numbers.
Right.
They always taught us that those were imaginary.
Well, that's where the power of abstraction really comes in.
Okay.
So let's just take a super simple example. 3 - 5.
Okay.
Seems impossible if we're only thinking about positive numbers, right?
Yeah, you can't take away more than you have, or can you?
Exactly. That's it. By abstracting the concept of subtraction, we open up this possibility of negative numbers.
Wow.
It was algebra that allowed mathematicians to invent a solution to this problem that seemed like it didn't have one.
So by sticking to those rules, we actually expanded what numbers could even be.
Exactly.
That's kind of mind-blowing.
It is, and it doesn't stop there.
Okay.
Take something like the square root of 2.
Okay.
We know it's irrational,
Yeah.
meaning we can't express it as a nice simple fraction,
Right.
but we can still manipulate it using the rules of algebra,
Yep.
just like any other number.
So the rules stay the same,
Yes.
even as the types of numbers we're using get more and more complex.
This is what Feynman means by generalization.
Okay, I'm starting to see how powerful this is.
Yeah.
But how do we go from these building blocks to something as complicated as trigonometry?
Right.
That just seems like such a giant leap.
It's all about recognizing these patterns and connections that emerge when we go deeper. So for example, imagine trying to calculate something like 10 to the power of the square root of 2.
I'm already lost.
Right.
How do you even begin to calculate something like that?
This is where mathematicians had to get resourceful.
Okay.
They realized they could break down this really complex problem into smaller, solvable steps by using something called logarithms.
Okay, logarithms.
Yeah.
Those always kind of seemed like magic to me.
They might seem that way, but they're a testament to the elegance of algebra.
Okay.
Imagine having to calculate 54 square roots of 10 by hand.
54 square roots of 10
Yeah.
by hand.
That sounds pretty rough, right?
That's rough.
It was. But that's exactly what a mathematician named Mr. Briggs did back in the 1600s. And those calculations became the basis of the first logarithm tables.
Okay, that's some serious dedication, but
Yeah,
why
I-
even go through all that trouble?
Because logarithms give us this amazing shortcut.
Okay.
They let us turn these crazy multiplication problems into much simpler addition problems.
Yeah. So it's like finding a secret passageway through this big mathematical maze.
Exactly. And this discovery really highlights a crucial point.
Yeah.
Algebra isn't just about like crunching numbers.
Yeah.
It's about finding elegant solutions by uncovering these hidden connections between these seemingly unrelated ideas.
Wow.
We started with simple counting.
Yeah.
And now, thanks to algebra, we have a tool for navigating the complexities of exponents and way beyond.
This is mind-blowing. We're really starting to see the true power of algebra, and it feels like we're just scratching the surface.
It's true.
But hold on tight,
Yeah.
because things are about to get even more interesting as we delve into the mysterious world of imaginary numbers.
Right.
Okay, so last time we left off, we were about to cross over into like the land of imaginary numbers.
Right.
And I gotta be honest, it still kind of messes with my head a little bit.
Yeah.
How can a number be imaginary?
It's a little bit of a misnomer, I guess.
Yeah.
But think about it this way.
Okay.
What if you're trying to find a number that when you multiply it by itself, it equals -1? What could that possibly be?
I mean, I'm kind of blanking on that one.
Yeah.
You can't have a negative square, can you?
Exactly. And for centuries, mathematicians basically said, yeah, that's it. We've reached the limit of what numbers can do.
Right.
But then someone came along and said, well, what if we just invent a new kind of number?
Okay.
And that's where this thing called the imaginary unit comes in. It's that letter I.
Right.
And it's defined as the square root of -1.
Okay.
Even though that seems like it breaks all the rules.
Yeah, it seems like we're just making stuff up now.
Right, exactly. But it turns out to be incredibly useful because
Okay.
this is where Feynman, I think, really brings it home.
Yeah.
He shows us that by introducing this I and keeping all of the rules of algebra consistent, we unlock this whole new dimension of mathematics.
A new dimension. So it's like we found a secret room in the house of math that we didn't even know existed.
Exactly. And in that room are these things called complex numbers.
Okay.
They're written as a plus bi, where a and b are real numbers, and then I is our imaginary friend.
Right.
So it's like this combination of the familiar and then this new sort of strange thing,
Yeah.
and it creates this incredibly powerful system.
So if we keep running into equations we can't solve,
Yeah.
are we going to have to keep inventing new types of numbers?
That's a great question. And where does it end?
The amazing thing is, according to Feynman, it ends here.
Okay.
We've reached the end of the line.
Wow.
With these complex numbers, we now have all the tools we need to solve any algebraic equation.
Wow, that's incredible.
Yeah.
But you did promise us a connection to trigonometry.
Right.
And I'm still waiting to see how these imaginary numbers play into all of that.
Here's where it gets really wild.
Okay.
Feynman takes us back to these complex powers we were talking about.
Right.
But this time he focuses on raising 10 to an imaginary power.
Okay. You're going to have to go slow with this one for me.
Okay.
We're dealing with imaginary exponents now.
It sounds crazy.
Yeah. But the rules still apply.
Okay.
And he does this clever thing where he realizes that 10 raised to a very, very small power is basically equal to 1 plus that power,
Okay.
multiplied by a special constant.
Okay. I vaguely remember this from calculus.
Exactly.
Yeah.
So he starts calculating these imaginary powers of 10.
Okay.
And he's putting them in a table.
Hmm.
And as he's doing this, he notices something really remarkable.
What's that?
The results start to oscillate in a very specific pattern.
Oscillate. You mean like a wave?
Like a wave.
Okay.
And not just any wave.
Yeah.
It's the sine and cosine function.
Right.
The building blocks of trigonometry.
Hold on. So you're telling me that hidden within algebra, within these imaginary numbers, is the key to understanding triangles and circles and all of that?
That's exactly what he's saying.
Wow.
And it all comes down to this incredible formula. He calls it the most remarkable formula in mathematics,
Okay.
which is e to the power of I theta equals cosine theta plus I sine theta. This single equation ties together the world of algebra, geometry, even calculus.
And we got here from counting.
And we got here from counting.
This is incredible.
It really is. It's like
Yeah.
we've uncovered this secret passageway
Yeah.
that connects all these different areas of math.
So we've gone from basic arithmetic to like the foundations of trigonometry and beyond,
Right.
all thanks to the power of algebra.
Exactly.
So we went from like counting on our fingers
Right.
to this mind-blowing formula that
Yes.
connects algebra and geometry and calculus.
It's pretty amazing.
It really is. It's amazing to think that it all starts with those basic building blocks, you know?
What's really fascinating is that this isn't just a story about math.
Right.
Feynman is showing us this, like, a way of thinking,
Okay.
a way of looking at the world that has implications far beyond equations and formulas.
So how does that apply to, say, like my everyday life?
Well, think about how often you run into a problem that seems impossible at first.
Oh, all the time.
Right.
Yeah.
It might be something at work, a situation with a friend, or even just trying to learn something new.
Right.
It's easy to feel stuck.
Totally. I've definitely had those moments where I'm like, I don't even know where to start.
And that's where I think the lessons of algebra can really come in handy.
Okay.
Remember that power of abstraction?
Yeah.
Instead of getting bogged down in the specifics of the problem,
Okay.
try to see like the underlying structure, the general principles that are at play.
So it's like zooming out and looking at the bigger picture instead of getting lost in the detail.
Exactly. And just like we use algebra to generalize from integers to these crazy complex numbers, we can apply that same principle to our thinking.
Okay.
We can start to see connections between things that seem totally unrelated,
Yeah.
find patterns and principles that show up in different areas of our lives.
So it's about finding those connecting threads, those like underlying principles
Yeah.
that tie things together.
Exactly. And it's about being willing to ask, what if? Just like mathematicians invented new types of numbers to solve these impossible equations,
Right.
we can use our creativity, our imaginations, to find new solutions to the challenges that we face.
It's like Feynman is saying, don't be afraid to push the boundaries.
Yeah.
Explore the unknown, even invent something totally new.
Yeah.
That's a really cool message.
And it all comes back to that fundamental curiosity,
Mhm.
that willingness to ask questions, to explore, to keep digging deeper. That's what drives us forward.
I love that.
It's math and in life.
This deep dive has been amazing.
Yeah.
It's not just about like understanding algebra,
Right.
It's about this whole idea of abstract thinking and generalization and finding those hidden connections.
And things that make the world a more understandable and really fascinating place.
Absolutely.
Mm-hmm.
So the next time you're facing a challenge, remember what we've learned here.
Yeah.
Embrace that power of abstraction. Look for those hidden connections and never underestimate the power of your own curiosity.
Well,
That's it for this deep dive. Until next time, keep exploring, keep questioning, and keep diving deep into the wonders all around us.